like I was introduced, I'm a senior scientist at Idaho National Laboratory, but before I came here, I worked for 32 years at NASA, and I retired in May of 2020. And one of the big projects I worked on was looking at the effects of microgravity on crystallization of Z-bland glass. And also, towards the end of my time there, I looked at the effects of an axial magnetic field on that crystallization. Now, just a little background if you're not familiar. Z-bland glass was discovered in the mid-70s by Marcel Paulin and Jacques Lucas at the University of Rennes. And it was really serendipitous. They were trying to form a single crystal and kept getting a glass. And what they found were very unusual optical properties. And as you can see from the figure, attenuation coefficient versus wavelength. Z-bland, there's a theoretical curve there, and also what has been measured to date versus fused silica. And one of the interesting properties of Z-bland is that it transmits from the near UV to the mid IR. And that gives it some obvious applications for sensors. It also theoretically has a much lower attenuation coefficient than fused silicas. And one of the things that was really investigated starting in the 80s was maybe replacing fused silica in long haul fibers for communications. But to date, that hasn't worked out. And I'll get into that a little bit. Z-bland does have a low optical attenuation coefficient, 0.01 dB per kilometer, and that's a couple orders of magnitude better than, or order of magnitude better than fused silica. Now, the heavy metal fluoride glasses have been studied for approximately 40 years. Z-bland has showed the most promise. Like I said, it transmits in the IR out to about 5 microns, and applications include fiber amplifiers, lasers, and nuclear radiation resistant links. It's been found that fused silica, say if you're using it as a sensor in a nuclear reactor, it darkens quite rapidly, whereas Z-bland is impervious to neutrons and gamma rays. It does form color centers in the UV, but those can be healed just by pulling the fiber out for a couple of hours, or you can use white light on them and it'll heal them. So it has that advantage. Band gap absorption, Rayleigh scattering, and multiphonon absorption, while extrinsic or impurities such as rare earth ions and crystallite formation. And the loss that has been achieved to date is due to intrinsic and extrinsic properties, processes. Now, it does have outstanding properties. It's a multispectral window, UV vis, IR, like I've spoken about earlier, no absorption peaks, it's low loss, low refractive index, it's low dispersion, low phonon energy loss, low DNDT refractive index with time, and the CTE is similar to stainless steel, so it has and aluminum, so it has assemblies reliability. If the coefficient of thermal expansions were different, that could lead to problems. Now here's a chart just showing transmission percent versus micron wavelength for a 10 millimeter thick window, and you can see that it transmits 100% of the value out to about 5 microns, and it starts dropping off. And here's transmission from the visible to the mid-IR. This is attenuation coefficient in dB per meter versus wavelength. And again, you see you start getting some losses when you get out into the mid-IR. Now, viscosity is very important. What I found out in my studies and previous studies is very highly nonlinear compared to fusel. If you plot log of viscosity versus 1 over the temperature, you can see them in the left-hand figure that for Z-bland is highly nonlinear over here versus fused silica, which is effectively linear. This nonlinearity leads to some viscosity or thinning of the material at certain temperatures, which can lead to crystallization. So I ran a number of experimental series, and the first one I did was I obtained Z-bland fibers from infrared focal systems and Bell Laboratories. And those fibers were stripped of coatings and were placed in evacuated quartz ampules. And these fibers were first flown on our NASA's KC-135 reduced gravity aircraft, also known as a vomit comet. And the aircraft produces approximately 25 seconds of reduced gravity per parabola. You also have to look at, when you go out of the parabola, you're going into the bottom of the parabola when you're coming out of the top. So you're going to get almost 2 Gs. So you're playing one against the other when you're doing your experiments. So 1 week of flights would lead to approximately 200 total parabolas. And the fibers were heated to the crystallization temperature during reduced gravity. And I compared them to unit gravity for the same amount of time. And after those initial experiments, I also flew on board fibers on the Conquest suborbital rocket. And that flight gave approximately 6.5 minutes of reduced gravity. And this is a little experiment I did. It was very inexpensive that I flew on the KC-135. And it consists of a push rod where you mount your quartz ampule with a fiber and a preheat zone oven. And what I'd do is I'd push the fiber in there before we got to the low gravity portion of the parabola, just to heat it up to the blast transition temperature, which is about 275 C for these fibers. And then as we went into the low gravity portion, I'd push it into this annealing zone, which was set at 340 C, leave it there for 20 to 25 seconds, and then put it into a quench. Very manual, but it worked. This is a Conquest rocket payload, and this one, we were able to mount 12 different fibers in here, and this was all automated. It acted just like the manual one that I flew on the KC-135, but this one was perfectly manual. It had your samples, translation stage, a quench assembly, and a heater assembly. And so it would go first up into the heating assembly once you get into the microgravity portion, and then into a quench assembly. And this is just an image. We launched this suborbital flight from White Sands, New Mexico. Now, basically what happened, the samples that were produced in 1G or unit gravity exhibited crystallization. And the sample on the left is a 1G sample. You can see the surface crystals here. And the samples produced in reduced gravity did not show any crystallization. We looked at this in scanning electron microscopy as well as X-ray diffraction. And another experiment I did was I had a buddy of mine at the local university built me a fiber draw system. And this basically consisted of a translation stage to push a Z-blend optical fiber preform down to a heating element, and then just heat the tip of the preform and draw down. This is I coated the fiber with an acrylic and then ran it through here and UV cured it, and then pulled it onto a take-up reel. This is just a couple of, we videoed this, and you can see the fiber on the left, 0G fiber is crystal free. However, when you started into the high G portion of the parabola, this measured 1.8 G, you can see the white crystals that formed. So what I basically had to do was, I couldn't draw continuously like I wanted to, because crystallization would occur and then the fiber would break. So I'd have to go in and break off the tip and start over. And so I just got short links of like, 30, 40 centimeters was all. Not enough to really measure anything other than look at the crystallization, but it did prove the concept. And nucleation growth rates are inversely proportional to viscosity. And a colleague of mine proposed shear thinning as a possible mechanism that would be present in 1G that's absent in reduced gravity. And it's been observed for polymer melts, but typically those were under high pressure where you saw the shear thinning. And basically, the mechanism states under conditions of shear thinning, the effective viscosity decreases with increasing shear rate. So you get these little equations here, and low gravity processing is known to reduce convection, which reduces shear, thus crystallization will be reduced in low gravity. However, we didn't observe any shear thinning. We ran a ground experiment and didn't see any. Mechanism, I feel like, was likely more subtle. The short range order of Z-blend glass is very similar to the barium zirconium fluoride crystals, which precipitate when it does crystallize. And my thought is that mild perturbations in the material can induce crystallization. And we're planning on testing this using electrostatic levitation and measuring the viscosity versus temperature. And it's proposed that the log viscosity versus 1/T will become more linear, thus extending the T sub X crystallization temperature minus the glass transition temperature range for Z-blend. Typically, T sub X minus T sub G for Z-blend is about 90 degrees centigrade, whereas for fused silica, it's several hundred degrees C. So that's the reason you do not see crystallization in silica, and you do in Z-blend. It's very difficult to draw fiber within that range unless you have extreme temperature control. Now, here's the Z-blend glass. Here on the left, the short range structure. These are the fluorines and the zirconiums here, and you have barium, sodium ions. Now, when you look at the barium zirconium fluoride crystal, what I tried to do here was show how the barium just shifts basically one interatomic spacing here. And that's all it would take to cause a crystallization to occur. So that's the reason I'm saying I think it's more subtle than some of the other proposed microgravity mechanisms. As far as electrostatic levitation, this is the Marshall Space Flight Center ESL facility in Huntsville, Alabama. That's where I worked. And here is a levitated Z-blend at 500 C. We use a 100-watt CO2 laser on this. And you can see where the laser is impinging here. And we were able to melt. However, we had difficulties with rotation of the particle, the sphere, which induced convection and induced crystallization. So they've added another, since I left, they've added a second CO2 laser to see if that helps. I haven't been able to run any samples as of yet. Now, present work in microgravity, there are 3 companies that have drawn Z-band fiber on the International Space Station. Made in Space, FOMS Inc. FOMS just stands for Fiber Optics Manufactured in Space, and Physical Optics Corporation. Some improvements have been made. The only problem is not enough fiber has been drawn to measure the attenuation coefficient yet. You really need a kilometer of fiber to get a good measurement, but several hundred meters might be sufficient, but they've only been able to draw short fibers. Now, magnetic field effects. Magnetic fields have been used to affect flows in conducting fluids. DC field tends to produce a body force that opposes or damps buoyant convection. For example, calcium carbonate crystallization decreases under a DC magnetic field. For the work I did, I used an axiomagnetic field, and that was based on a theory by Chandrasekhar in his book, Hydrodynamic and Hydromagnetic Fields. This theory shows that the gravitational perturbations in a conducting liquid jet can be stabilized in an axiomagnetic field. In this case, the Lorentz force is absent. Here, B is the applied magnetic field and J is the current density. So what I did is had the same guy that built my payloads for the KC-135 put together a solenoid magnet. It had a field strength of 0.1 Tesla. And he made it so that we could reverse the magnetic field direction by changing the polarity of the power supply. He added a furnace that was inside the magnet, and it could go to 400 C. And the furnace, like I said, was mounted in the center. And fibers were placed in fused quartz ampules and backfilled with helium to aid in heat transfer. And it also protects the fibers from water. One of the issues with Z-band is it's not only oxygen can cause, or air can cause crystallization, but water vapor can cause crystallization. So you have to, it's a non-oxide fiber, so it has to be protected. And we set it up so the fibers were aligned with the solenoid axis. And this is, it's a very simple, inexpensive experiment. This just shows it set up in the lab that we had. Here's the magnet with the furnace and the temperature controllers, and of course the helium gas bottle. So what I did is I heated the samples to 345 C for 45 seconds with a magnetic field parallel to the gravity vector. Okay, and then I heated in other samples, same conditions, except where the magnetic field anti-parallel to the gravity vector. And then control samples were heated to 345 C for 45 seconds with no magnetic field. So after processing, the samples were observed with stereo-optical microscopy, SEM, and X-ray diffraction. And the results, the control samples with no B field showed surface crystallization. You can see that on the left fiber. The samples heated parallel to the gravity vector showed irregularities. That's a sample in the middle, but no crystallization. And the sample on the right is with a magnetic field anti-parallel or opposed to the gravity vector, showing no crystallization. So we basically got the same results on the ground as we did in microgravity. And I hypothesized that the mechanism for the suppression of crystallization was due to the permeability difference between the amorphous glass and the crystallites. And you can write the equation here for the change in free energy without a magnetic field And here R is the radius of the nucleus. Here's your bulk free energy, delta G sub V. And epsilon is the strain energy increase per unit volume. And when you apply a magnetic field, the free energy for formation of critical nucleus is derived in this equation. And H is the intensity of the applied magnetic field. Mu sub 2 is the permeability of the crystal. Mu sub 1 is the permeability of glass. Unless you have two measurable quantities, magnetic field intensity and permeability difference. Now, if permeability of the crystal is less than that of the glass, then the energy will be lowered and crystallization suppressed. So what we did is we measured the magnetic susceptibility for crystallized and amorphous Zeeland glasses, and the dimensionless volume magnetic susceptibility is defined by M equals chi H, where M is a magnetic dipole moment per unit volume, and chi is a magnetic susceptibility. And then we calculated, or I calculated, permeability using that equation where U is the permeability of free space. And what I found was there was no significant numerical difference between the calculated permeability values, so I discarded that possible mechanism. Now, in semiconductor melts, for example, flow velocity is attenuated and viscosity increased above a critical magnetic field intensity, about 0.1 Tesla. At crystallization temperature, viscosity is approximately 10 to the 4th poise, which will allow ionic diffusion. An increase in viscosity would slow diffusion and thus crystallization. So what I need to do, and I'm waiting on funding for this right now, is to investigate the higher applied magnetic fields. Now, for what to look forward to, what we're working on, this is just a drawing. It's from a patent of mine for an orbiting fiber draw facility. I'm a big believer in robotics, particularly in space, and this would use a 3-axis robot. In this case, you have a preformed storage area on the extreme right. You can take those preforms, and not all preforms are crystalline free, so you could wrap them in platinum and nickel and heat those up and actually melt them at 800 C and get rid of the crystals, and then cool them down. And then you have a grinding and polishing station to remove those metal coatings. And then you actually draw the fiber, and the robot would do the actual drawing, the fiber initiation, and do a take-up reel, and then you'd have a storage area. So this could all be done, calculated for an 8-meter long facility. You could draw 1,000 kilometers of fiber and store it. And you could use something like SpaceX's old a type of Dragon capsule to come get those. So you could keep the facility in low Earth orbit. It'd be a lot safer and less expensive than drawing in the space station, for example. Another idea, this is to propose to draw a Z-band optical fiber through an axiomagnetic field. And this is just what a typical draw tower looks like, with a preform feed, your preform, a draw furnace, a fiber diameter monitor, coating cup, coating oven, a diameter monitor, and a capstan or a take-up reel. And the electromagnet would be placed just below the draw furnace. And I have designed a magnet that's variable between 0.1 and 1 Tesla. So we could test those and see what kind of things attenuation coefficients we get out of it. So, for drawing through an axial magnetic field, the two hypotheses would be tested. One that will yield fiber with a decreased attenuation coefficient by suppressing crystallization. The other is the axial magnetic field will align spins in the atoms, preventing clustering, which leads to crystallization. And I would test that with electron spin resonance. So in summary, both microgravity and an axial magnetic field suppress crystallization. Mechanisms are unknown at present, may be similar for those or different. Electrostatic levitation experiments will give an understanding of viscosity versus 1/T. And drawing the fiber through an axial magnetic field should lead to lower attenuation coefficient based on previous work. Excuse me. And electron spin resonance should give information on the mechanism for this method. I believe that is it. Thank you.